we've seen how we can use the first derivative to help understand about what's going on at a critical value. The next thing that we want to do is try a different way or see an alternative approach that involves the second derivative, because instead of just understanding whether or not a function is increasing or decreasing, if we just understood whether something was concave up or concave down at a critical value, that would also tell us whether or not there was a maximum or minimum. Because remember what a concave up and concave down piece or interval of a curve look like. If it's concave down, it looks like a bowl turned upside down. If it's concave up, it looks like a bowl turned up. Further, if we know that we have a horizontal tangent at the top or the bottom of that, which is what a critical value would be, also would apply to something that looks like this, something that looks like this. And we know that we have, we wouldn't have a second derivative here, but these are other places that we would find critical values. We can tell that it's going to be a maximum or minimum just by the shape. You know, is this a bowl upside down or a bowl right side up, like maximum or minimum? And again, the second derivative will tell us that. So we have a function, we find its critical points, and then we evaluate the second derivative at that critical point to see if we can tell what kind of a critical point it is, whether it's a maximum, a minimum, or neither. So let's use just two basic functions here, x to the fourth plus 3x squared, negative x to the fourth minus 3x squared. Again, we need the derivative, so 4x cubed plus 6x. I need to know where this thing equals 0. So where does 4x cubed plus 6x equal 0? Well, wherever x times 4x squared plus 6 equals 0, that's going to be at x equals 0. And if I just cursory glance at this, you'll subtract 6 and divide, and you'll have a negative number. There's no square root of a negative number, so the only critical value here is at x equals 0. All right, these are not real numbers. We're only interested in real numbers for now. Okay, so our critical value is at x equals 0. Now, we could look on both sides of that to see whether it's increasing or decreasing, or we could evaluate the second derivative. And if we look at the second derivative, we get 12x squared plus 6. We plug 0 in, we get 6. So f double prime at 0 is 6. What does that tell us? That tells us that at 0 or around 0, the graph looks like this. So this must be a minimum. And that's our second derivative test. Okay, we'll do the same thing with our other function. Hopefully you recognize that this is just this guy flipped, so we should hopefully determine that this is a maximum. And take our first derivative. Negative 4x cubed minus 6x. Solve for where this equals 0. We'll find the same thing, same reason, just at x equals 0. Now let's find our second derivative of x. Well, the second derivative of g with respect to x. Negative 12x squared minus 6. If we look at the second derivative at 0, this will be 0. Minus 6 is minus 6. It's negative, so the graph looks like this there. Hence we have a max. Okay, and that's what we expected. Just knowing that if we put a negative out in front of this thing or change these signs, it's just going to flip it upside down and we get a maximum. Right, and that's our second derivative test. So again, we'll go through next how we can use the computer to verify that.